If your sweat's at body temperature, why does your sweat cool you down? Let me introduce you the concept of latent heat. Latent heat is the energy added or removed during a phase change, where temperature stays constant. So a phase change is, for example, going from a solid to liquid through melting or evaporating from liquid to gas. So freezing, condensing, all of those things involve latent heat. And temperature does not change during the phase change because energy goes into breaking or forming molecular bonds, not speeding up motion. So you could add heat to ice and it won't get hotter. It will just sit at 0 degrees Celsius and melt into water. The energy from the heat that you're putting onto the ice isn't lost. It's just not put into temperature. It's put into breaking molecular structure and turning it into liquid. The formula that represents this is Q equals ml, where Q is the energy that's absorbed or released, M is mass in kilograms, and L is the latent heat constant. There's a latent heat constant for fusion, aka melting and freezing, and there's a latent heat constant for vaporization, which is boiling or condensing. And these are on the free cheat sheet in the description, and here's some must-know values. So the fusion latent heat constant for water is 333,000 joules per kilo, so melting and freezing. For boiling and condensing, which is the vaporization one, for water is 2,260,000 joules over kilos. This means that it takes 7 times more energy to boil water than to melt ice, even though the temperature is the same the whole time. When would you use this equation? You use it during any phase change when the temperature is flat. So if temperature is holding constant during energy transfer, you use latent heat. For example, melting or fusion, which makes ice go to water, or vaporizing, which makes water into steam. It also ties in with kinetic theory. At melting point, the energy doesn't increase kinetic energy, which would increase temperature. It's used to overcome the attractive force between particles. So if you got all your particles in your thing, all attracted to each other, the energy at melting point, the particles loosen up. So that's why the particles fully escape into gas. It's why the vaporizing latent heat constant was way bigger than the fusion one, because escaping requires way more energy than sliding. So when you're boiling, your particles are not just shaking faster, they're breaking out. That's where your energy goes at the melting point, not to temperature. It goes here to change it from one state of matter to another. A real life application of this is when you sweat. So this is you and you're on a jog. When you sweat, the water absorbs energy from your body to evaporate. The energy is taken away as latent heat, so your body cools down. Let's go through a problem. Here's the situation. You have a block of ice and it's sitting at 0 degrees Celsius. It weighs 0.4 kilos. How much energy do you need to fully melt it into a puddle of water without raising its temperature? We're going to use our formula. So we're only doing a phase change because temperature stays constant. And since we're melting it from solid to liquid, it's a process of fusion. Let's simply plug in our values. So the energy we need to add to the system is equal to the mass, 0.4, multiplied by the latent heat constant for fusion, which, if you remember for water, is 333,000. This gives you 133,200 joules of energy. So what that means is that is the amount of energy that you got to add into an ice cube to fully melt it before raising its temperature. All of this energy is going to go into breaking down the particles into a different shape. Here's the second problem. You're boiling water in a pot. There is 0.25 kilos of water and it's already at 100 degrees Celsius. How much energy is required to fully evaporate all of the water into steam? Let's check out our formula again. There's Q equals M times the latent heat constant for vaporization, because we're boiling the water. So you know when to use fusion and you know when to use vaporization. I'll put it on the cheat sheet in the description. Let's plug in our values. So the energy required to fully turn this water into steam is equal to the mass times this latent heat constant for water, which was 2,260,000. Final answer is 565,000 joules of energy. This will vaporize the water. Notice something. Our ice block from the earlier problem took 133,000 joules. And this ice cube was 0.4 kilos. It's heavier than the water. But this water, to boil it, we needed nearly 4 times more energy. Vaporization drains energy like crazy. Final insight I'll give you in this video is that latent heat is invisible energy transfer. There's no temperature change, but massive energy costs. You don't notice it by touching whatever object it is, but it's doing the real work to make phase changes happen.